we're going to review how to determine the energy terms and levels that are available to quantum mechanical systems, namely atoms. So we're going to start by considering the case in which we have one electron per orbital, as would happen in the excited state of an atom. So we'll look at a simple case where we just have two different electrons, and then we'll also look at what happens when we have more than two electrons, all in different orbitals. So let's start by considering the 2p1, 3d1 configuration. To determine the available terms, what we need to do is make a Clebsch-Gordan series with our L's and with our S's. So we have to determine what the L and S values are for these individual electrons. So our first electron here is in a p orbital. So our L1 is equal to 1 for the p orbital, and the S for electrons is always equal to 1/2. Our second electron is in a d orbital, so its L is equal to 2, and its S is also equal to 1/2. To determine the energy terms and levels, we need to know the capital L and capital S. So to figure that out in this kind of scenario, our capital L is going to be equal to, and this is the Clebsch-Gordan series coming in here, it's L1 plus L2. And then we take the series down, so then we go L1 plus L2 minus 1, and we keep going until we get to the absolute value of the difference between L1 and L2. So in our case, with L1 is equal to 1 and L2 is equal to 2, our L1 plus L2 is equal to 3, and our L1 minus L2 is equal to 1. So our possible values for L here are 3, 2, because we take integer steps down in between our maximum and our minimum value, and 1, which is the minimum. We do the same thing for S, and you can see that that's going to be 1/2 plus 1/2 is equal to 1, and then 1/2 minus 1/2 is equal to 0. So our S is equal to 1 or 0. And now to determine the terms that are available, all we have to do is simply combine these numbers. So we'll have a 3, 2, and 1 L term, each with a singlet and triplet, a 1 and 0 S term. So remember, our L is a number that goes from 0, 1, 2, 3, and it continues on. And those get symbols akin to our orbitals. So an L of 0 gives a capital S, and a L of 1 is P, L of 2 is D, and L of 3 is F, and then it goes on G, H, I, however. So our available terms here are going to be L equals 3, which is a F term. So we have a 3F term. And the way we write the symbols again is going to be 2S plus 1 L. So our S is equal to 1. That gives us a 3 up there. So we have a 3F term, a 3D term, a 3P term, and then a 1F term, a 1D term, and a 1P term. Now, what if we have more than one or more than two electrons? We can't simply make this series. So for example, what if we have a 2p1, 3p1, 4f1 configuration? Well, in this case, what we're going to do is just take two of our electrons and calculate L in the way we had before, and then we are going to combine that maximum value of L with our third small L. So I'll show you what I mean. So we'll look at all our L's. So here, our L is equal to 1, 1, and then our 4F orbital has an L of 3. So we're going to construct L of 1 and 2 based on our first two electrons here. So that is going to be 1 plus 1 is 2, and then 1 minus 1 is 0. So our possible capital L values are 2, 1, and 0. And then our actual L is going to be made of this 2 and our 3 here. So our actual L values are going to be what's 3 plus 2? Well, it's 5, and 3 minus 2 is 1. So the available terms, the available L's are going to be 5, 4, 3, 2, and 1. And there's not going to be a 0 term because we're just combining the maximum value from our first L with our next small L. S is simply going to be 3 halves because we have 3 electrons. So our S value is going to be 3 halves, and then we take an integer step down, and it's 1/2. So those are our two possible values for S. And so then the available terms will be the combination of these S's and L's. So that gives us a 4H term, a 4G term, a 4F term, a 4D term, and a 4P term, as well as a 2H, 2G, 2F, 2D, and 2P. Now, if you actually were to go and figure out what terms there are, there's a lot of degeneracy, and there's many 2G terms and many 4F terms, and so on as we go about this. All right. So that's how we can do this if we only have one electron per orbital. But if we have multiple electrons in the same orbital, their position actually influences the other one. So if you have a spin up, if you have a spin up in, say, L equals -1 or ML equals -1, you can no longer have another spin up in L equals -1. So to figure out how many or the configurations available, if we have many electrons per orbital, we have to actually go ahead and figure out the states that are available and assign them to terms. So what we're going to do here is we're going to look at a 3D2 configuration. And there are 45 possible states, and I have 45 states here listed out for the 3D2 configuration. And we can simply fill these out. So the best way to do this is just to start at the beginning, fill up, and then spin down, and then continue to assign the electrons. So we can go spin up, spin up, spin up, spin down, and we'll assign the electrons in this way. And I'm going to go ahead and do it here pretty fast, and I encourage you to follow along, pause the video, and then do this on your own. Now, once we've assigned all of the spin ups, we'll switch and start with the spin down here. So we'll go spin down, and so on. And so we'll assign all of the electrons to all of the states in this way. All right, so I'm going to pause the video here and fill this out, and then resume in a second once I have it all filled out. All right, so now you can see that I have this whole chart filled out. Hopefully you can follow along and fill one of these charts out for yourself. Once we have our charts filled out, the next thing we want to do is assign an M sub L and an M sub S to each of these states. So the M sub L is simply the sum of all the little M sub Ls, and we have these values down here. These are our M sub L values. So if there's an electron in that first slot, that has an M sub L of equal to 2, and so on. And this is relatively arbitrary, but of course the d orbitals, there's 5 different d orbitals, and they have, each one of those corresponds to one of these different states. So when we're considering all the states, we can just pick whatever we want and pick one line to be 2 and one line to be 1 and so on. And then the ms is going to be the sum of the small ms's, which is simply the spin up or spin down. So in this first case, both of our electrons are in the ml equals 2. So we sum that, and our capital ML is going to be equal to 4. One is spin up and one is spin down. So our ms is equal to 0. And so what we'll do is we'll just go ahead and fill this out in the same way as before. I'm going to pause the video, fill these out by simply summing their position. So I'll do another couple before I pause the video. So the next one down, we have a small ml equals 2 plus a small ml equals 1 is an ml equal to 3, and they're both spin up, so that has a value of 1. And the next one, they're in the same d orbitals, but one is spin down now, so there's an ms equal to 0. So we can go through, fill out this chart in the following way, and once we have that, we're going to be able to assign terms. All right, so now we are coming back and we have all of our ML and our MS values calculated for each state. So to figure out the terms that are available, what we're going to do is figure out the maximum ML value and then figure out the maximum MS value that goes along with that, and assume that those are our maximum, or that those maximum MLs correspond to the capital L, and then the maximum MS corresponds to capital S. So if we fill our chart out in this way, the place to look is at the top. So we can see at the top here, we have our maximal ML value of 4. So I'm going to come down here and say our ML max equals to 4. I'm going to change color. So our ML max is equal to 4. And the maximum MS associated with that, right next to it, you can see is 0. And there's no states that have a ML equals 4 with an MS equal to 1. So we're going to assume then that our L is equal to 4 and our S is equal to 0. And then we need to decide what states we should see with this term. So if L is equal to 4, that means our ML should go from negative L all the way up into L, including 0. So our ML should be 4, 3, 2, 1, 0, minus 1, minus 2, minus 3, minus 4. And S equal to 0, of course, has no steps, so our S should always be 0. So we should have ML values that all have an S equal to 0. And we can find that. So here's one example. We have a 4, 0, 3, 0, 2, 0, 1, 0, a 0, 0. And then we're looking for a minus 1, 0, a minus 2, 0, a minus 3, 0, and then a minus 4, 0. So all of these states belong to this term, which is going to be a 1G term because S equals 0 and L equals 4. And now we go ahead and do the same thing again. So now our next ML max is equal to 3, and it has an MS max equal to 1. So this is consistent with the state of L equals 3 and S equals 1. So that means we need states that have ML equals 3, 2, 1, 0, minus 1, minus 2, minus 3, and an MS of 1, 0, and minus 1. So let's go ahead and find those states. We have a 3, 1, a 3, 0, a 3, minus 1, a 2, 1, a 2, 0, a 2, minus 1, a 1, 1, 1, 0, 1, minus 1, a 0, 1, 0, 0, 0, minus 1. Now we should have a minus 1, 1, minus 1, 0, minus 1, minus 1, a minus 2, 1, a minus 2, 0, a minus 2, minus 1, and then a minus 3, 1, minus 3, 0, minus 3, minus 1. And again, so this state is corresponding to a 3 for our S and then a F for our L, so a 3F state. Let's do it again. What we have now is we have an ML equal to 2 with an MS equal to 0. So that's going to correspond, we're going to do the same thing. It's going to correspond here to a 1D term. And what we're going to need is a 2, 0, a 1, 0, a 0, 0, and then a minus 1, 0, and a minus 2, 0. After that, what we have left, you can see we have an ML max equal to 1 with an MS equal to 1. And by the same process, we'll get that this corresponds to a 3P term. So then we're going to find our 1, 1, our 1, 0, 1, minus 1, 0, 1, 0, 0, 0, minus 1, and then minus 1, 1, minus 1, 0, minus 1, minus 1. And all that's left over now is a 0, 0, which is corresponding to a 1S state. Or a term. So the terms that are available in this 3D2 configuration are a 1G, 3F, 1D, 3P, and 1S state. Now, how do we rank them? We're going to use Hund's rule to rank these, and Hund's rule states that the lowest energy term has the highest spin degeneracy. So that's going to be either our 3F or our 3P term has the highest degeneracy. And now if they have the same, Hund's second rule is that the one with the greatest orbital angular momentum is lowest energy. So that's going to be our F here. So to rank these terms, we'll have 3F is the lowest in energy, followed by 3P. That's followed by 1G, 1D, and finally the 1S term has the highest energy. Now there's one thing I haven't yet talked about, and that's energy levels. So to figure out the levels involved in a term, we need to figure out what J is. So J is equal to L plus S, and then just like we've seen to figure out our L's and S before, it takes this Clutch-Gordon series. So we go L plus S minus 1, and then we take integer values all the way down to the difference between L and S. So now that we know how to figure out our J, we can figure out the levels that are involved in these systems. So let's start with our 3F term. So our 3F term has an L equal to 4, or sorry, an L equal to 3 because it's F, and an S equal to 1 because it's a triplet state. So our possible J's there are going to be 3 plus 1. So our largest J is 4, and then that can go all the way down to 3 minus 1, which is 2. So our J's that we could have are 4, 3, and 2. And then we can do our same thing for our 3P term, which has an L equal to 1 and an S equal to 1. So those J's will be from 2 down to 0. Now, since the rest of our terms are singlets, what we'll see, we'll look at our singlet G here. What's available, so our G, L is 4, but our S is 0. So the only J's possible for that are 4. And same thing with our singlet D and singlet S terms. With S equal to 0, we actually only have one level. So what we can see is that if our S is equal to 0, so for these singlet states, there is only one level in the term. And the same thing would go for our S down here. If we have an S equal to 0, there's also only one level in those terms. So that will split our system, our 5 terms here, into 3, 4, 5, 6, 7, 8, 9 different levels. So we write the levels as 2s plus 1 L, and then we put a J as a subscript. So our 3f term would be split into 3f4, 3f3, and 3f2 levels. Our 3p term would be split into 3p2, 3p1, and 3p0 levels. And our remaining 3 terms would not be split into different levels. We could write them as 1g4, 1d2, and 1s0 levels. This is where Hund's third rule comes in. So we can use Hund's third rule to talk about the differences in energy levels, and it depends based on whether or not our orbitals are more than half filled. So for us, our orbitals are less than half filled, which means the lower J is lowest in energy. So our lowest energy level here would be our 3f2 level. Now, if our orbitals were half filled or more, it switches, and then we would go up to the highest energy. So if we were working with a 3d8 configuration, our 3f4 would be the lowest level. So now at the end of this video, hopefully you have a good idea for how we can go about determining the energy levels and states in terms that are associated with a given quantum mechanical configuration.